Well, thanks everyone for joining us today. This is the next segment of AI statistics and data science in practice. And today we have Dr. Frank Wei as our speaker. He is currently the principal AI ML scientist and director of data scientists at General Motors, where he's putting large language models into production using the Python packages VLLM and TensorRT for different business cases based on prompt engineering, retrieval augmented generation, and low rank adaptation. Dr. Wei has been with GM for 6 years, and prior to his work with large language models, used machine learning, data mining, and deep learning approaches to build L3 autonomous driving high definition maps based on vehicle telemetry data and images. Prior to joining GM, Dr. Wei served as a senior research statistician at the US Department of Agriculture, where he also focused on AI ML, specifically deep learning, generative adversarial models, earlier generations of natural language processing, named entity recognition and information extraction, including BERT and long short-term memory methods. Dr. Wei holds a Master's of Arts in Applied Mathematics and a Master's of Science in Applied Statistics from the University of Michigan. He received his PhD in Computational Science and Data Science from George Mason University and was a postdoc at NISS from 2013 to 2014. I had the good fortune to meet Frank through his service on the NISS Affiliates Industry Subcommittee, that's helping to stand up this webinar series. So today, Frank's going to be talking to you about architecture for putting large language models into production. And I'm going to turn it over to Frank now. You can go ahead and share.
Yes, sure. Thanks, Nancy, for the great introduction. I'm honored to be here just to make a presentation for the work I have done. And welcome to this presentation on large language models, a transformative force in artificial intelligence. And the topic I'm going to talk about today is large language model, transforming AI, and machine learning. Over the next 1 hour, we will explore the evolution, architecture, and operational frameworks of LLMs, as well as their real-world applications, from their theoretical foundations to their impact on different industries like healthcare, finance, education, e-commerce, so on and so forth. LLMs are reshaping how we approach natural language processing and machine learning. This talk will also include a demonstration of an LLM-based solution, showcasing how these models address complex challenges. By the end, we will have a comprehensive understanding of LLMs, their significance, and their potential to revolutionize AI. Let's dive in. Large language models are AI systems trained on vast amounts of text data, enabling them to understanding and generate human-like language. These models have become the backbone of modern AI applications, powering chatbots, virtual assistants, and content generation tools. Their availability to process and generate text with minimal human intervention has led to widespread adoption across industries. The growth of LLM-powered solution is driven by increasing enterprise adoption, expanding APIs, and cloud-based AI services, marking a significant shift from traditional NLP methods. The journey of NLP began with rule-based systems, relying on handcrafted linguistic rules and domain expertise. The introduction of machine learning brought statistical models, improving pattern recognition, and transitional NLP to data-driven approaches. The rise of deep learning and neural networks, particularly word embeddings and recurrent neural networks, revolutionized NLP by enabling representation learning. Milestones like sequence-to-sequence models and neural machine translation further advanced to the field. Today, unsupervised and self-supervised learning dominate, with models pre-trained on massive text corpora eliminating the need for task-specific feature engineering, and advanced in computational power, including GPUs and TPUs, have been instrumental in this revolution. The development of LLMs has been marked by several key milestones. Word2Vec introduced embedding-based models, capturing semantic relationships in vector space. Sequence-to-sequence models enabled efficient translation and text generation. BERT revolutionized NLP with bidirectional learning, while the GPT series popularized autoregressive text generation. Text-to-text transfer transformers unifies diverse NLP tasks under a text-to-text framework. And models like Llama, Claude, and DeepSeek have pushed the boundary of fine-tuning efficiency and inference speed. These advancements highlight the rapid progress in LLM research, driven by innovations in model architecture, training techniques, and computational resources. Each milestone has contributed to the growing capabilities and applications of LLM. LLMs are built on the foundations of neural networks and deep learning, which enable multi-layer architectures for representation learning. Self-attention mechanisms, a core component of transformers, allow models to capture long-range dependencies in text. Gradient-based learning, powered by backpropagation and optimization algorithms like NM, form the backbone of LLM training. Transfer learning, where models are pre-trained on large datasets and fine-tuned for specific tasks, has been pivotal in NLP. This approach reduces the need for labeled data and improves performance in low-resource settings. Additionally, the shift from statistical n-gram models to neuroprobabilistic methods has enabled LLMs to exhibit emergent properties, such as unexpected generalization ability and improved performance with scaling. The LLM architect landscape is dominated by industry leaders like OpenAI, Google DeepMind, Meta AI, Anthropic, and DeepSeek, which develop both proprietary and open source models. Open source initiatives foster community-driven innovation, while proprietary solutions focus on commercial optimization. LLMs are driving AI-driven automation, enhancing business operations, and accelerating research in different fields. However, their social impact includes workforce transformation with potential job displacement balanced by new AI-driven career opportunity. Ethical considerations such as bias and fairness are critical challenges. Looking ahead, LLMs are expected to integrate further into everyday human interactions, evolving towards multimodal AI models that combine text, vision, and other modality. And transformer is one of the most important architecture, or we can call it the foundation of the large language model, which represents a significant evolution from RNNs and LSTMs, addressing limitations like sequential processing bottlenecks and vanishing gradients. The core component of the transformers are including the multi-head self-attention, feed-forward network, and residual connections. And the transformers is in an encoder-decoder structure, which enable tasks like merging translation and the text generation possible. while attention mechanisms solve long-range dependency issues. Transformers are pre-trained on vast text datasets and fine-tuned for specific applications, offering superior performance in NLP tasks. Their adaptability across diverse AI domains has made them the foundation of modern LLMs. Real-world implications include improved translation, summarization, and question answering system, showcasing the transformative power of transformer-based architecture. Self-attention is a mechanism that allows transformers to assign different importance to words in a context, enabling the contextual understanding across non-texts. It operates by scoring the relevance of words through dot product mechanisms and applying softmax normalization. This process improves language modeling, particularly in tasks like translation and summarization, by reducing dependency length constraints. Unlike traditional sequence models, self-attention enables parallelization in training, eliminating the need for recurrence operations. However, it comes with computational trade-offs, such as high memory requirements. The intuition behind self-attention lies in its ability to compute a weighted sum of input values per token, adjusting based on learned parameters to capture contextual relationships effectively. Diagram often shows interactions between query, key, and value vectors, mapping words in a sentence using attention scores. And this is a visualization that gives a more elaborate explanation for attention mechanism, so that attention is spread out to different words to make the prediction to the word we would like to. Transformers lack inherent sequence awareness, requiring explicit positional information to process the text order. The original architecture uses sinusoidal functions to encode positions, allowing models to generalize to unseen sequence lengths. These encodings are added to token embeddings, providing unique signatures for each position. Alternatives include learned positional embeddings, which adapt to task-specific patterns but increase model size. Relative position encodings, which focus on distance between tokens, have gained popularity for tasks like translation, so on and so forth. Recent innovations like Levy attention with linear biases improve extrapolation to long sequences. Key considerations include balancing fixed versus learned encodings and managing memories usage for long documents. Multi-head attentions splits the input into multiple subspaces and performs the attention on each of them. Each head learns distinct attention patterns, such as syntax, semantics, or coreference resolution. This parallel processing improves representation power and robustness, as the model isn't reliant on a single attention mechanism. Benefits include faster training through parallelization and better generalization across diverse linguistic features. However, increasing the number of heads beyond 8 to 16 often yields diminishing returns. Recent optimizations like grouped query attention reduce memory usage by sharing keys and values across heads.
Frank, sorry, can I interrupt for a moment? I'm sorry, we had a question from our audience that I just saw. It's in the chat. I'm going to ask people to move your questions over to the, not move them if they're already there, but if you have a question, please put it in the Q&A. I'm sorry, I didn't get that said at the beginning of the meeting. Frank, this question came in a minute ago, and it was about DeepSeek. So the AI app called DeepSeek, you mentioned it a slide or two ago, has been at the top of the news recently. Does DeepSeek have features that apps like ChatGPT do not have?
Well, I like to say both of them are generative models, which just generative answers based on the questions asked. So the long story short, basically, they are all generative models, but just in different frameworks.
Thanks. I appreciate you answering that for our audience. If others have questions, please shoot them in the Q&A, and I'll ask Frank as he let him get back to his presentation now.
Okay, sure. Thank you. Yep, thanks for a great question. The encoder and decoder architecture is fundamental for sequence-to-sequence tasks, like translation and summarization. The encoder processes input text into context-rich representations, while the decoder generates output tokens conditioned on these representations. Cross-attention mechanisms link encoder outputs to decoder inputs, enabling tasks like machine translation, so on and so forth. Variants include encoder-only models like BERT for classification and decoder-only models like GPT for generation. Unified architectures like use the same parameters for both encoding and decoding, improving versatility. And then some other unique features and techniques introduced by transformers are a layer normalization. So for layer normalization, stabilize the training by normalizing activations within each layer, reducing the internal covariate shift and improving gradient flow. So operation involves scaling and shifting activations using learnable parameters. Feed-forward networks transform attention outputs through nonlinear transformations, enabling complex pattern learning. These networks typically consist of two fully connected layers with a ReLU activation. Key insights include the importance of normalization placement for training stability and the role of feed-forward networks in introducing nonlinearity. Recent work shows adaptive normalization techniques can further improve convergence, especially for large models. Scaling law reveals the predictable relationships between model size, data, and performance, guiding the development of larger and more capable models. The Chinchilla paper demonstrated that optimal performance requires balancing model size and training data, with 20B parameter models trained on 1.4 T tokens outperforming large, less trained models. Key findings include diminishing returns as models grow and the importance of data scaling for continued improvements. Practical implications include optimizing resource allocation and avoiding over-parameterization. Recent work suggests this law may break down beyond 1T parameters. Hinting at fundamental limits, understanding scaling law is crucial for making informed decisions about model development and balancing performance gains with computational cost. LLMs follow a two-stage training paradigm, pre-training on massive text corpora and fine-tuning for specific tasks. Pre-training objectives include masked language modeling and causal language modeling. Fine-tuning adapts model to tasks like sentiment analysis for question answering. Parameter-efficient methods like LoRa and adapter reduce fine-tuning costs by updating only a subset of the parameter. Instruction tuning aligns model to follow human instructions, improving zero-shot performance. Key LLM architectures differ in their training objectives and application. GPT models optimized for text generation, a BERT designed for classification, and the text-to-text transformer unifies tasks under a text-to-text framework. Performance trade-off includes GPT's super generation capabilities, but slower inference, and BERT's faster processing, but limited to classification. Recent innovations like sparse model improve efficiency, while multimodal models extend capabilities to text and vision tasks. Practical insight. Choosing the right architecture depends on the task. GPT for generation, BERT for classification, for versatility. Understanding these differences is crucial for optimizing performance and resource usage. And of course, everything comes with a cost. And the challenge in transformer-based models are, of course, high computational cost, energy consumption, interpretability, scalability is very difficult, and also like we need tons of the data. And of course, ethical concerns like the bias, fairness, so on and so forth. For summarization, the key innovation of the transformers are self-attention, position embedding, scaling, so on and so forth, which enabled the unprecedented language understanding and generation. And for the futures, which is also happening now, is sparse models we could have and multimodal architectures and efficiency improvements. Transformers are the foundation of the model, of course. Yep. I was spending the first 20 minutes talking about the architecture of the transformers and the transformer-based large language models. And for the next session, I'm going to talk about how large language models are different from the traditional machine learning models development pipeline. Traditional machine learning pipelines involve several stages: data connection, feature engineering, model training, evaluation, and development. Data connection requires curated labeled datasets, while feature engineering involves manually extracting relevant attributes. Model training uses supervised learning on engineered features, and evaluation relies on metrics like accuracy and F1 score. Deployment integrates model into production systems. Challenges include scalability as manual features don't generalize well, and maintenance as drift requires frequent retraining. Domain expertise is critical for feature engineering, but this reliance limits adaptability. LMs disrupt this workflow by automating feature extraction and enabling transfer learning, reducing the dependency on labeled data and domain expertise. This shift allows model to scale across tasks and domains, though it introduces new challenges in computing requirements and interpretability.
Frank, I have another question for you from the audience, if you're ready to take one. Okay. Can we encode numerical data to be text data and utilize already trained large language models to perform prediction? For example, if we have spatiotemporal data that comes in the form of images at times t, t+1, t+2, so on, can we encode the images into text such that the encoding includes the spatial and temporal dependence, and then use an LLM to forecast spatial temporal data into the future without having to train a model? That's a tough one.
Yeah, it's a very good question, to be honest. And it would be very difficult for me to answer this question like in a few minutes. Would that be possible if the audience could email me the answers and I could answer probably by email after the session, because like I still have a lot of slides left, and spending too much time on answering the question would give me probably not enough time to finish all the slides.
Sure. I'll put Frank's email into the chat, which he approved before this meeting, so that you can send that question directly to him to get a longer answer to that. Thank you.
Thank you. Traditional NLP systems struggle with several key limitations. They often fail to capture long-range dependencies, relying on n-grams that miss broader context. Generalization is poor, as models overfit to training data and struggle with unseen vocabulary. Multilingual support requires language-specific feature engineering, making adaptation costly. Scalability is limited, as manual features don't adapt well to new domains. Complex tasks like summarization and translation are particularly challenging, with traditional methods producing incoherent or inaccurate outputs. LLMs address these issues by learning representations directly from data, capturing context through attention mechanisms, and scaling across languages and domains. This shift has enabled breakthroughs in tasks requiring deep contextual understanding, though it comes with increased computational costs and complexity. The rise of LLM represents a paradigm shift from feature engineering to end-to-end learning. Instead of manually crafting features, models now learn relevant patterns directly from raw text. Deploying LLMs require robust operational frameworks to handle data pipelines, model serving, monitoring, and versioning. Data pipelines must process large-scale text data efficiently, while model serving architectures need to support low latency inference. Monitoring tracks model performance and detects drift, ensuring reliability over time. Versioning manages model updates and experiments, enabling reproducibility and rollback if issues arise. Key tools include MLflow for experiment tracking and TensorFlow for serving for deployment, and so on and so forth. Best practices include implementing CI/CD pipelines for model updates and using canary deployments to test new versions. These frameworks are essential for maintaining the performance, scalability, and reliability of LLMs in production environment. LLM deployment strategies vary based on application requirements. Cloud-based solutions offer scalability but raise data privacy concerns. On-prem deployments provide greater control and security, but require significant infrastructure. Hybrid approaches balance scalability and control, leveraging cloud resources for peak loads while keeping sensitive data on-prem. Considerations include latency for real-time applications, cost for large-scale deployments, and security for sensitive data. Recent trends include edge computing for low latency applications and federated learning for privacy-preserving training. Choosing the right strategy depends on the specific use case, balancing performance, cost, and security to meet business needs effectively. And evaluating LLM requires comprehensive metrics, including accuracy, robustness, fairness, and efficiency. Accuracy measures task-specific performance. while robustness assesses consistency across inputs. Fairness evaluations identify biases and ensure equitable outcomes. Efficiency metrics track computational resource usage. LLMs demand specialized computational infra, including GPUs and TPUs for parallel processing, high bandwidth memories for large models, and fast interconnects for distributed training. Optimizing the strategies include model parallelism, which split model across devices, and pipeline parallelism, which overlaps computation and communication. Mixed precision training speeds up computation and reduces memory usage. Effective model versioning ensures reproducibility and reliability in LLM deployments. A model registry centralizes storage for different versions, while metadata tracking logs hyperparameters and datasets. Rollback mechanisms allow reverting to stable versions if issues arise. Best practices including using semantic versioning, maintaining detailed documentation, and implementing A/B testing for new releases. Tools like DVC for data versioning control and MLflow for model lifecycle management streamline these processes. Proper versioning and lifecycle management are essential for maintaining model performance, enabling continuous improvement, and ensuring compliance with regulatory requirements. LLMs have fundamentally reshaped deployment pipelines, moving from feature-based systems to end-to-end learned representations. Traditional ML pipeline required extensive feature engineering and domain expertise, while LLM automates all these steps, enabling faster development and deployment. However, this shift introduces new challenges, such as how to manage a large-scale infra and optimizing for inference efficiency. Cloud-based deployments offer scalable but raise data privacy issue. And as we discussed before, and also on-prem solution gives us more privacy, but it's more expensive. These changes reflect the broader transformation of AI systems driven by LLMs. And LLM could not only be used as a tool to accelerate the traditional machine learning pipeline, but also can be used as a tool for the product as well. For example, prompt engineering. Prompt engineering optimizes LLM outputs by crafting effectiveness input queries. Techniques include zero-shot prompting, where the model generates responses without examples, and few-shot prompting, which provides a few examples to guide the model. Chain of thought prompting encourages step-by-step reasoning and improving performance on complex tasks. Instruction tuning frames tasks like instructions, while template design structures prompts for consistency. Challenges include sensitivity to phrasing and difficulty in controlling output style. Iterative refinement helps improve prompts over time. And another application for large language model is RAG, retrieval augmented generation, which enhances large language models by combining their generative capability with external knowledge retrieval by embedding user queries and retrieving relevant documents. RAG ensures responses are grouped in evidence while maintaining natural language generation. Key applications including advanced question answering, document summarization, and personalized content creation. However, challenges like balancing relevance with accuracy and avoid hallucination require careful implementation. To maximize effectiveness, fine-tuning document embeddings, regularly update knowledge bases, and ensure context consistency between retrieval and generation. RAG is a powerful tool for unlocking the full potential of LLMs in real-world scenarios. And also, as I mentioned before, everything comes with a cost. Security considerations, like we have the risk of the data leakage. We have the prompt injection attacks, a bias amplification, privacy violations, misinformation generation, and adversarial manipulations. And LLM raise significant ethical concerns, including bias, fairness, and transparency, as some of them were mentioned in the last slide. Bias in training data can lead to skewed model outputs, while fairness issues arise when models disproportionately impact certain groups. Transparency is challenging due to the black box nature of LLMs, complicating efforts to explain decisions. Regulatory frameworks like EU AI Act are emerging to address these issues. Best practices including algorithmic audits, diverse data curation, and tools like SHAP and LIME for interpretability. And the environment impact of LLMs is a growing concern as well, because of the huge energy consumption.
Frank, a few questions have accumulated for you in the chat. Are you okay with taking those now?
Yeah, sure.
Okay. One of them goes back a slide or two and asks, what would you suggest for validating large language models with no labeled data for research purposes?
It's a very good question. And there are several things probably we could do with regard to that. And first, of course, is probably just use the open source data for evaluating the large language model, particularly the large language based models you would like to choose. Second, I would like to say use a large language model, use another evaluator to evaluating the performance of the generation result.
Okay. Frank, a couple of the questions in the chat are about how you do things at GM. Are those questions you're open to taking, or should we skip those? Really asking about how things are done.
Oh, I would leave that for later on, and
Okay.
also can we at least skip it for now?
Sure. And then there's a philosophical, well, I don't know if it's philosophical. It's a deep question. Will large language models ever achieve an understanding similar to human cognition, or are they inherently different?
I get
That's
in
another
my
tough
point.
one.
Yeah, it's a very I like to say it's a very difficult one. I would like to say, after all, large language model is a probability model. Everything is based on a probability. And this is completely different from how human beings is functioning, at least based on the research we learn at the moment. So long story short, how large language model performs is completely different from how human brain performs. And no matter how powerful the large language model is, it's really difficult to just compare them to.
Thank you.
Yeah, and I'm sorry for the limited time that I have to answer the question in such a short version. And if an extended answer is preferred, I like to answer the question through email.
Thank you.
The environmental impact of LLMs is a growing concern, with training large models consuming significant energy and contributing to carbon emissions. And the future LLM research focuses on innovations like reinforcement learning with human feedback, multimodal AI, AI agent, and personalized systems as well. Despite these advancements, LLMs face open challenges, including scaling limits, robustness against adversarial attacks, and factual consistency. Scaling laws suggest diminishing returns beyond certain model sizes, while adversarial attacks exploit vulnerabilities in model inputs. Factual consistency remains an issue, with models sometimes generating incorrect or nonsensical outputs. Aligning models with human values and ensuring ethical behavior are ongoing concerns. Okay, and like we have covered the foundation, and also the application of LLMs, but all of them are just knowledge. And now we are going to dive into one of the products the team and I are working on, the Job AI, the AI-driven career enhancement. The goal of this product is provide an assistant, particularly the assistant from the AI side, for updating resumes, crafting cover letters, and preparing for interviews based on the mock interview, and for the of course on the specific job descriptions. And the scope of it, and also the target clients are job seekers, and also for the companies or teams who are looking to hire professionals as well. So it could be the job seekers as well as the hiring managers or hiring professionals. And the competitive advantages are dual market leverage, efficiency, and precision in tailoring application materials, comprehensive preparation for job applications and interviews. And basically, there are two functions within the product. The very first is the resume cover letter update based on the input or the user's write-up, resume, and job description. We generate, or the product generates, the customized or the tailored updated resume with specifically to the specific job. The second function, chatbot, prepares the users with the interview by giving them the mock interview question and evaluating how good they are doing, which is an interactive service. And if we are using the traditional machine learning pipeline for this application or for this product, like we have to use the processes listed on this slide, which is including more than 10 surveys and models, and which is a huge workflow. And by using the large language model-based solution, we are cutting off at least half of the process so that we can save a huge time and huge costs. And here is a more elaborate architectural design form for our product, for our LLM-based product. And let's break down how this product delivers precision, scalability, and dual market values for our clients. User interaction and security layer. Our users and interacts with the product through a robust security layer. This layer ensures data privacy and seamless access via Streamlit for intuitive user interfaces, API gateway, and Lambda for serverless, scalable request handling, containerized environments to isolate sensitive operations. Every input, whether a resume, job description, or chatbot query, is securely routed through this layer, guaranteeing compliance and reliability. Core AI engine, LLM service, and NLP modules. And the heart of the system lies our deployed LLM service, augmented with specialized NLP modules. Text preprocessing cleans and structures raw inputs, resumes, job descriptions. Information extraction identifies key skills, qualification, and experience from a document. Text classification categorizes content for tailored recommendations. And summarization and conference resolution refines outputs for clarity and coherence. These modules enable the product to dynamically align user profile with job requirements, generating optimized resumes and cover letters. Three, knowledge base and vector database. Vector database utilize embeddings to enable semantic search, rapidly retrieving contextually relevant information. This combination ensures the AI doesn't just process text, it understands context, delivering hyper-personalized outputs. 4, recommender systems and workflow integration. The recommender folder orchestrates final outputs through language generation, draft natural sounding cover letters, and resume bullet points. Final formatting ensures document adhere to professional standards. And as for the chatbot service, real-time interactions are powered by interactive guidance, validating user inputs and clarifying ambiguities, personalized suggestions, pulling insights from the LLMs and database to refine the advice. And the data persistency and scalability, where all user data and generated artifacts are managed via the database layer, handled read and write operations for resumes, cover letters, and user profiles. And file systems stores documents securely, enabling the easy retrieval and version control. And why this architecture wins and why this product succeed is because the same AI engine serves B2C users and B2P clients. Precision and scale, vector database and LLMs ensures recommendations are both accurate and context aware. And end-to-end security, from private containers to API gateways, data integrity is never compromised. This architecture isn't just a technical blueprint, it's a backbone of a product that transforms job seeking and hiring into a seamless, intelligent experience. And while we were looking at the current blueprint and current architectural of the product, here comes how the components would be approached by traditional machine learning. And you can see that the process are doubled by adopting the LLMs. So So you can see that how LLMs could change the landscape of the machine learning world at the moment.
Frank, you're
Key takeaway.
someone from the audience. If there's another question for you, and this one's about whether you ask your users if they got hired or not as a result of the feedback, and then incorporated that feedback into your chatbot.
Oh, so this chatbot is only designed for helping the users prepare the interview by providing the mock interview questions and evaluation. So there's no hiring decision will be made based on the chatbot. So it's just a tool, an interview preparation tool, if that makes sense.
Okay. Another question from the audience. What are the key differences in a custom resume rewriting product from providing the job description and draft resume to general chat GPT or Gemini and requesting a resume rewrite?
So basically, go ahead, please.
No, that's it.
Oh, yeah, sure. And so basically an advantage of our tool is we are tailored the user resume based on the job description as much as possible so that we could possibly help the user to pass the first screening or the screening of the HR process. That the resume could be handed to the next round. So that's our goal and purpose.
Thank you.
Sure. Yeah, so today's key takeaways highlight how our product revolutionizes job application preparation. And the core functionality, the system efficiently tailors resumes and cover letters to match job descriptions, boosting candidates' competitiveness. Chatbot integration offers real-time guidance, ensuring accurate data entries and personalized suggestions to refine materials. Together, they create a seamless workflow, streamlining the application while maintaining high-quality output. Look ahead, future steps focus on enhancing the chatbot with adaptive AI, expanding the features like interview prep and multilingual support, and building a user feedback loop for continuous improvement. Scalability remains a priority to ensure robust performance as we grow. This roadmap ensures we stay ahead in transforming career readiness. In conclusion, LLMs present a transformative force in AI, reshaping how we approach natural language processing and machine learning. Their architectural innovations, operational frameworks, and real-world applications demonstrate their potential to solve complex challenges across industries. However, ethical considerations, environmental impact, and open challenges remain critical areas for future research. Yeah, that's all of my presentation. And thanks everyone for coming. And back to you, Nancy, if there's any questions. Yeah.
We do have another question from the audience. This one is, do you have any concern that increased use of large language models will reduce the amount of original material, effectively reducing new data large language models can train on, potentially resulting in large language models cannibalizing on their own output?
Yep, I'd like to say that would be an issue because nowadays there's a new trend that more and more people are using large language models for the generation task. Basically, like they do not write things by their own. And I still remember, like there was a time when I was back into the office and I read the emails sent by my colleagues, and I found most of them are somehow modified by large language models. Yeah. So, and I couldn't imagine like how many raw materials are going to be generated by human beings in the future. So the concern is valid, and there is a trend that we are going to use more and more of the generative AI to generate not only the text, but images, and probably future and for other use cases that the real data is going to be less and less, so that the only thing the large language model could find to be trained on is the data generated by themselves. So it's just calling it a cycle, but who knows?
So another one, follow up on that question. Do you have any thoughts on how to avoid that problem?
I guess the question I'm going to ask is, do we need to avoid this problem? Like everything has two hands. So basically, like, even though we have less and less raw data, we could be using to train our data, to train our model, or we're going to live in a world that is surrounded by large language model. If we are getting used to the world that is generated by large language model, it is good. But if we're not, we have to find the ways to break through, just to break through the room which is created by generative AI. And there should be a way, and there must be a way, but we have to work very hard to find it.
Frank, I have a question. You brought up the issue of the energy that it takes to train these large language models, and of course, that's got environmental implications. But have you seen any studies of, I guess, the cost of large language model text compared to human generated text? Which, when we're generating it ourselves, we think, oh, it's so much work to generate this text, but we're not paying for the energy in most cases to build the model. But trying to understand, what's, some kind of cost comparison on the cost of AI generated text versus the cost of human generated text.
Yes.
Just my own philosophical question that goes back to your, takes a lot of energy to train these things.
Yeah, yes. And this is a very good question, to be honest, Nancy. I like to say, the energy consumption by using the large language model is like, it uses not only tens or 100 or 1,000 GPUs, but combined it uses just more than tens of thousands or even 100,000 GPUs for the training and inference purposes. And the energy consumed by the process could be used by human beings for all the actions for hundreds of years. So the energy consumed by human beings is way less than the energy consumption from the large language model related service. Yeah, so and that's basically the reason why the energy consumption issue is becoming one of the concerns for the community.
Yeah. Yeah, I would like to see that analysis. You also have to account for all of the, not just the energy it takes us to write something, but our whole lives have to be supported so that we're there to write it. So yeah, just that would be an interesting comparison. There's another question. We're running out of time, so let's do this as the last question. Is there a concern about government purging or censorship of information or data sets that are being trained on, i.e. health data in the US right now? And there's kind of a follow-up question that's in that same, it's a slightly different vein, but how can RLHF play a role here in curbing the misinformation? So 2 questions, sorry, throwing them at you at the last minute.
Well, that's a very difficult question, I like to say. And I'm sorry, like the connection was a bit cut off. Would you mind, or would you mind repeating the question? Or
With the time we have left, how can RLHF play a role in curbing misinformation?
in curbing this,
Curbing.
I'm sorry, my
In
sorry, my internet was
reducing misinformation.
misinformation of.
I think can large language models help find misinformation?
Can large language model help finding the misinformation? Am I hearing that correctly? I'm sorry, like my internet, my connection was a bit cut off.
Yes,
Okay,
that
sure.
you're hearing the question correctly.
Oh, that's awesome. Yes and no. Based on I like to say it all depends on the context. Because like the large language model is trained on the vast amount of data, basically the text we could imagine of in the world. So if the context or the misinformation appears previously, or it has a some trend we could find from other documentations, yes, we could fill in the misinformation by large language model. But if this is a zero-shot problem, if this information has not occurred or appeared in other documentations, I would hesitate to conclude that this information would be found, could be identified or could be found.
Okay, well, it's 4:03. We were just scheduled for an hour today. Thank you, everyone. And thanks, Frank, for giving this presentation. It was very informative on how much evolution there's been recently in large language models. And everyone have a good day.
Thanks, Nancy. Have a good one, everyone.